Welcome everyone. This is a webinar on discrete global grid systems. Starting with some introductions, my name is Emmanuel Stefanakis, and the panelists or speakers for today are Peterson, Erin, Lee, Marta, Padilla, Ruiz, and David Bowater. It is our pleasure to be here, and we are all affiliated with the Department of Geomatics Engineering at the University of Calgary. So Calgary is located in Western Canada. It is 9 a.m. right now, a good time for a webinar for us, a good time for probably the Americas, not that good time for Europe and Asia and Australia and Africa. But this session is also being recorded. So Calgary is known as the Canada's energy capital because of the big oil and gas industry in the province of Alberta. It is also known for the Rocky Mountains. The mountains you see at the back of this picture here, a very beautiful place to visit. Calgary is also known for the University of Calgary, which is located here, and the Winter Olympics of 1988. So the University of Calgary and the Department of Geomatics Engineering at the University of Calgary was founded in 1979, and it is an international leader in education and research in geomatics engineering. It is one of the 4 geomatics engineering programs in Canada. In fact, it is the biggest program in geomatics engineering in Canada. So our team is part of the working group 7, Commission 4, which is about Geo-Data management. And we are offering this webinar on behalf of this working group. So here is the outline of 5 presentations given by our speakers. We start with we're going to start with Marta presenting presenting what a discrete global grid is. Then Perry is going to give a demo with some Canadian data and see how we can manage and visualize and analyze data using discrete global grid systems. We follow up with Erin and David, who are going to present us research directions in discrete global grid systems and research outcomes from our research group. And finally, Perry is going to give a vision for discrete global grid systems. So as these presentations are going through, the Q&A will be open, so you can type your questions there. We may interrupt the speakers to answer these questions, or we can always have, so we have allocated some time at the end of this webinar, a question period. So this webinar is going to last about an hour. With the question period, it will be something about 1 hour and 15 minutes. So with that, I will pass it over to Marta to give an introduction to discrete global grid systems.
Thank you, Emmanuel. Can you see the presentation? Yep. So, hello, my name is Marta and Padilla Ruiz, and I'm a PhD candidate at the University of Calgary. I'm going to give a brief introduction about what is DGGS. So the current paradigm around geospatial information is that we definitely have lots of geospatial data, but the problem is that there is not only one format or source, there are many of them. And we have made our best efforts to make the data open and accessible. We have OGC standards, public compliant APIs, web map services, etc. And now users can access the data. However, there is still an evident gap for end users seeking geographic knowledge to make better use of it and get meaningful information from the data. So clearly, open access to the data is not enough. Geographic data is very complex, comes from various sources, and combining different data sets has always been a challenge in geospatial. So end users still require intermediate assistance by GIS experts to be able to combine and analyze the data they have access to. So current GIS technology takes all this big data into an analog model of the Earth using latitude and longitude coordinates on conventional grids, and sometimes projects these coordinates into projected coordinate system. And the data is treated as a layer model, where each layer represents a set of information like roads, land use, boundaries, etc. And the data is then processed by a GIS expert to perform the data integration and analysis. And after this process is when services, APIs, and knowledge is produced from these intermediate products. So to simplify the process of spatial analysis for non-GIS experts, we need to reinvent the concept of GIS and produce analysis-ready data so we can provide services and products on the fly and make better and quicker decisions. So this grand challenge of geographical data integration can be solved by using a discrete global grid system, which is a digital multi-resolution model that can integrate data on the fly across all types of scales, projections, and to an actual global reference. So what is the definition of DGGS? A discrete global grid system is a spatial reference system that uses a hierarchical tessellation of equal area cells to partition and address the globe. So it is a multi-resolution system with each cell having a unique identifier or indexing. And an important aspect about this hierarchy is that cells at the same resolution are equal area cells on the surface of the Earth. So the system is defined to be an informational grid, not a navigational grid. So information integration, decomposition, and aggregation can be optimized in the hierarchical structure, which is exploited to support data processing, discovery, visualization, analysis, and modeling. An important mention is that DGGS has become an international standard, not only in the geospatial world, with the OGC publishing an abstract specification in 2017, but also the ISO published part 1 of the discrete global grid system specifications last year. And the United Nations mentioned DGS in the Global Statistical Geospatial Framework as a common geography that will ensure that all statistical data is consistently geospatially enabled and user can discover, access, integrate, analyze, and visualize statistical information seamlessly. So how are these DGGS systems defined? There are a series of design choices needed to be made to construct the DGGS. First, you need to select a polyhedron to model the Earth's surface. Also, its orientation related to the Earth and the way the polyhedron will be divided into cells and how the partition of these cells will be performed in subsequent resolutions. Also important is to select the projection that will be used to project this polyhedron and its cells onto the Earth so we can perform transformations. So first, the polyhedron selection. They all start from regular polyhedrons called the platonic solids. They are convex regular polyhedron in the three-dimensional space, and their faces are regular polygons made for triangles, squares, and pentagons. And there are only 5 such polyhedrons shown in the picture. And these polyhedrons are used to model the globe, here represented as a sphere. And there are also other types of polyhedrons called the Archimedean polyhedra. They're semi-regular instead of regular, so they combine different polygonal faces, providing a better fit to the sphere. And the one that provides the best adjustment is the truncated icosahedron, constructed by taking the Platonic icosahedron and truncate the 12 vertices, ending up with pentagonal and hexagonal faces, the usual soccer ball picture. And the faces of this polyhedron are projected to the globe by a spherical equal area projection. And this is one of the design choices needed to be made, since it will define the transformation from and to the Earth's surface. And the orientation of the polyhedron relative to the Earth has an impact on the efficiency of the indexing and introduces deformation and inaccuracies, since it affects how the Earth gets partitioned. So this orientation is also a design choice achieved by the rotation and or translation of the polyhedron. And if working on a local scale, the study area would benefit from being in the middle of a single polyhedral face. As you can see in the picture, the right side of the picture portrays Canada in the middle of a polygonal face. And then these spherical projected polyhedrons get tessellated into equal area cells, and only triangles, squares, and hexagons provide a regular tiling of the sphere. And the results look something like this. Each tessellation have different properties and advantages depending on the application, but essentially squares are familiar, triangles are fast, and hexagons are defined as fit. And remember that the tessellation is hierarchical, so the cells get subdivided in each subsequent resolution. And there are different methods to subdivide the cells in these resolutions called apertures, each of which have different properties since they generate different patterns of cells. In the picture, you can see an aperture 3 hexagon cells and an aperture 4 with different patterns of cells. So to summarize the process of building DGS in a picture, first you start from the polyhedron, oriented the way better fits your needs. Then this polyhedron is subdivided into cells of a particular shapes and in multiple resolutions. And it is projected into the Earth with an equal area projection that you choose. So at the end, each of these cells in each of the resolutions needs to be uniquely indexed. Hierarchy-based space filling curves and access methods of indexes have been used to uniquely address cells. And the most common indexes methods are the ones who provide the nearest neighbor, fast linear ordering, and parent-child relationships. And indexing types can generally be transformed from one to the other. So to summarize the advantages of DGGS, cell locations are fixed at a certain resolution level. So the spatial data associated with a cell is aligned. And this is what we call congruent geography that allows for accelerated data queries since the data is already aligned. The cells are equal area, the same resolution. So each cell has the same probability to contribute to a spatial analysis. It is a multi-resolution system by nature, and the resolutions are defined with cell indexes. So multi-scale analysis can be carried out easily. The data model is globally uniform and allows to integrate geospatial information from various data sources, and it's independent of the original data formats, both vectors and rasters. And it is a system that considers the Earth curvature. So at a global scale, it will achieve a better analysis accuracy compared to projected coordinates. And the information is portrayed without huge polar distortion since it's uniform. DGGS are discrete systems instead of continuous coordinates. And this has an advantage since an aerial unit in a discrete system can model uncertainties around a location, while in continuous coordinates, you cannot do this. And finally, the cell indexes in the system are discrete and independent from each other. So they have the potential to be distributed and parallelized in cloud computed environments. And this is it from me. I will pass it to Perry, who will talk a little bit more about DGGS and will show a nice demo. Thank you.
Thank you, Marta. That was a very complete description of the DGGS. So my part of the presentation is actually to present a operating discrete global grid system. This one is called the PIXIS DGGS. But before we get to that, I just want to emphasize what Marta has mentioned here, that the critical problem that we have is the ability to integrate data quickly in conventional GIS systems across a plethora of different data types, projections, formats, scales, resolutions, etc. And often we have applications that are requiring us to bring in 2 or more data sources, and the DGGS is a choice to be made to integrate those. This also gives us some ability to hand over the data integration process from a professional to somebody that's not as familiar with the nuances of how to bring data together. So I'll talk about that towards the end of our talk today. So what I want to do now is to go to a demonstration. Give me a moment here to set this up. So we have here a visualization scheme. It's a rendering of an ophthalic sphere, so an area spherical, but the area of a WGS ellipsoid. And we're going to project onto that, as Marta has mentioned, from an icosahedron, an hexagonal cells onto this spherical surface using a projection that was developed by John Snyder. Hence it's called an icosahedron Snyder equal area aperture 3 hexagonal grid. So I'm going to bring that up here now. So this is the ICEA 3H. The projection of these cells here are really so that we can visualize it, you know, through our browser. But these cells, the information that's stored in these cells is much smaller than these cells that we're seeing on the screen. Just want to emphasize that, because sometimes when we're showing discrete global grid, there's this idea that these are big, huge cells and we're sampling the data in these big cells. But in fact, in the small cells that I'm showing you on the screen here right now, there's about 256 cells that would be sampled, and about 2 million on my screen right now if we're bringing in raster and vector data and aggregating that data. So if I zoom right down to where this is kind of topped off here, we're looking at cells now on the surface of the Earth about 2 millimeters apart. So we could be mapping localized data. I think David's going to show some of that. Be looking at regionalized data, and we can be looking at global data all at the same time, and we can be querying that data. I like to think of it as where GIS is really good at breaking information up into layers or themes of data. As Marta pointed out, discrete global grids are really good at bringing all that data back together again. So as an example, I'm going to bring some data into this discrete global grid, this ICEA 3H global grid, so that you have an idea of how that can happen. In the application here, we can connect to a variety of services, service connections to RESTful services, to Earth observation data, to statistical, spatial data, local data that you might have. And I'm just going to have a little bit of a choice here. I'm going to bring in, to begin with, some political boundaries. Now, these are vector data. This happens to be a shapefile, an Esri shapefile. And it's reading that in, and we'll start to project that on our screen. I'm going to take the grid off here for a moment, so we just have a sense of where we are here. So because we're coming to you from Canada, I'll orient the globe so we're looking at Canada. And these are just, they look like vectors on our screen. If I zoom in really quickly, you might actually see this hexagonal cells sort of forming there. So yeah, so we're actually, just like a vector image would be projected a line on a graphics card as pixels, cells on your computer screen. We actually have a pixelization of the Earth's surface using a DGGS. So this grouping now, because this is a polygon, I can do a selection of Alberta. This is the province in which our university is located, and I can select that, and it can aggregate all of those cells and any information in those cells, and it tells me that the area based on that rasterization is 672,000 square kilometers. That's the size of the province that we're studying in. So what about data integration? What does that actually mean when we say data integration, fusion, data fusion, combining data sets? I thought I would use elevation models as an example where we can let's bring in several elevation models from different sources and see how those get integrated. So let's start out with a global elevation data. This is a 30-second data, G-topos 30, familiar. It's just a land cover data set. So we're bringing that in now. I'll zoom out to the whole globe. We can see we've just filled up cells with data values, elevation data values, and rendered those. I pre-rendered them so that we could see them on the screen. If I right-click on this, I'm actually sending a query to that elevation data, and it tells me that at that location, there's a cell, tiny cell, that's holding a value of 799 meters. If I moved over into the mountains here of Colorado, I know it's Colorado because I've got the political boundaries on there. It's giving me all those attributes at the same time. They were indeed in a higher location there, 2,801 meters. Now we could also bring in bathymetric data. The GEBCO data set is also has a terrain, terrestrial data associated with it. And so let me bring that one in here. There it is. So a second elevation data set source here. This is has some bathymetric data. So if I click and query that cell over in the ocean there, it's running through lots of data, and hopefully it'll come up with some data values here for me really quickly. There's nothing in the elevation for the terrestrial data set because there wasn't any coverage there. But in the bathymetric data set, of course, we're below sea level, 3,967 meters. If I click on land, back in Alberta here, wow, that's interesting. We have both elevation 657 and 657, but I don't think that's guaranteed. These are two different models. So I click a little bit different location and we see 780 and 816. So these are integrated data sources. We've just fused two different data sources. We do all our querying based on those different data sources. As an example here, I could reselect Alberta again as a polygon. It can aggregate all of those cells, and it tells me that the average elevation based on the terrestrial GEBCO data set is 773 meters, while the other data set, whoa, pretty close, within 100 millimeters, about the same. That's actually pretty amazing. But we see the maximum and minimum are a fair bit different. So that's a bit of data integration. What about, can we add some more? So let's add some more elevation data here. We have in Canada a tiling system that we get from the federal government of digital elevation models. It's called the Canadian Digital Elevation Model, CDEM. I'm going to add one of those, and it's just a small tile of information, and we'll bring that in here. It's very small, so I'll zoom to that location. And there's a tile in here, but it's been stylized the same as the terrestrial G-topos 30. I'm going to just change that so that I have a different recoloring. Just make it monotone and see if that shows up then. There it is. So we couldn't really see that before because that was really integrated right into our data source. And again, if I right click here, now I have 3 different elevations. They should be pretty close. Sometimes they'll be exact, but no, they're not. 1,151, 1,147, 1,150. And we would know, you know, the folks that are working with data like this all the time know that there's going to be a little bit of difference. There's precisions and there's accuracies of these data sources. What about LiDAR? It would be cool to bring some LiDAR in because it's highly detailed. I have some LiDAR data as well that I can bring in. So here's my LiDAR data. So I've got the 3D terrain, all integrated 4 different elevation data sets there, and that would show me how we can integrate 4 similar kinds of data sources, but we also had the vector data set as well in there. I'll just do another query through this and see if we can get, maybe I'm zoomed in a little bit to get the coarser data. Again, lots of data in here now, and I'll see it querying through there. There's the LiDAR. It's actually to the nearest millimeter, similarly. Okay, so that's kind of part 1 of my demo. That's just kind of show you how that integration works. And let's take the integration of various data sets. I'm going to pop some of these elevations off because they really help us visualize. There's lots of data. One of the things about DGGS is you get lots of data in here. We're really interested in spatial analysis, so asking questions of all of that data as it gets integrated. It's not always easy to see when you stack on data, so I'll just add a few more data sets. Let's think of other data that would be of interest at this regional level. Might be population, one of them. So we'll bring in some population data. Crops would be another one. Maybe some climate type data. So let's start with population. I think I have a population data set here. So this is coming in from Columbia University. Season, they have a server and it's a gridded data set itself of population, rectangular grid. And it's they've acquired that data from our census, Canadian Census Ministry, Stats Canada. And so I can click now on at a location and I get the population of that cell that I sat in. That's a density, 3,469 people per kilometer. And that's in Edmonton, the capital of our province. And down here in Calgary, downtown, we have 602, for example. But we can now do that same selection idea of the whole province. And let's select the whole province. And now we get this population distribution for the whole province, about 12 people per square kilometer. So not densely populated by any means. And we also have this ability to sub-select with a DGGS. So let's say I wanted to find out, you know, how many people live above 1,000-meter elevation in the province. So I could, you know, set a distribution on the elevation. I can say sub-select on that, and that's that elevation there, that it's above 1,000 meters. And we find that primarily because Calgary is in that set. We have about 27 people per square kilometer. Of course, if I multiplied that by the area that I've generated there, I would have the amount of people that are located. We could add some more data just to make it interesting. Let's add some superficial geology. Let's add some annual precipitation. Add some global land cover. And you can see things are getting pretty messy in our globe. But this just kind of gives us some sense then of things are going on. We have a distribution of, I had an indexing here of the different land types, and we have water, 658 square kilometers of water. We have the annual average precipitation in that area, 569 millimeters in depth, etc. We can look at different surface geologies. It's going to calculate that. These are just different attributes on a vector data set. And here we have, if you knew the coding for that surface geology, you'd have some understanding of that. So I think that should give people a general idea of how that DGGS works. Just keep in mind the really small pixel or pixelizing information. It's really sort of the equivalent of a digital model as opposed to an analog model of the Earth. So that's why it's called a discrete global grid system. Somewhat like the creation of digital music or digital video, where we're quantizing and sampling data from sound into a digital structure, and then you gain all the advantages, some of them Marta mentioned. So I will, I think we're passing this on to Erin now, or is it David?
I think, thank you, Perry. Excellent demo, and I'm always enjoying seeing that. Yeah, so I would like to bring your attention to one of the, So I would like to bring your attention to one of the DGGS applications we've been looking into. That is the quantization, analysis, and application of terrain data modeled in DGGS. I'd like to start by talk a little bit about the background information of the terrain data sets in Canada. So there are two main open source terrain data sets. They are the CDM, Canadian Digital Elevation Model, and High Resolution Digital Elevation Model. And they do have some main differences, and that would potentially cause some problems to the end users, especially if they would like to integrate them. For example, they have different coverage across the country. The vertical and horizontal datums are different. And they also have inconsistent horizontal resolutions across the country. And the water bodies have been treated differently, and they do have different accuracies. So the research problem we've been facing can be summarized from two perspectives. From the perspective of Canadian terrain data management, as I just mentioned earlier, there are multiple data sets that the end user can choose from. And if they like to use both of them, they probably have to go through heavy pre-processing. And they may end up with inconsistent results because the different ways they could use to pre-process their data sets. And more importantly, from the perspective of DGGS applicability, there's limited development of analytical algorithms, and it's still in the nascent period to support decision-making in the real world. So here are three research phases of my own research. The first thing is we're gonna integrate the data sets, the multi-source data sets into the DGGS. Then we develop analytical functions based on the terrain data we quantized on the DGGS. Then we apply that in a specific application domain. Here we propose to do flood mapping in the DGGS. Before we dig into the details, I'd like to talk a little bit about the existing DGGS libraries. So here are just a few examples of the current existing DGGS libraries, and most of them are open source. But the one that Perry just presented is not, it's commercial. And we have a little bit comparison summarize of a few examples in our recent paper. So I put it here if someone would like to have a look later. And for my own research, I use the Discrete library. And specifically, I use the art binding of that library called Discrete art. And as Marta introduced earlier, there are multiple DGGS configurations that one can choose from. Here I use the ICS3H in my own research. Here I stands for ectohedron, and SEA means the Snyder equal area projection. H is the hexagon, means it's the cell geometry used in this tessellation. And 3 is the aperture, means the refinement ratio between each two successive levels equals to 3. And we set the orientation with these parameters so that Canadian border is centered in one single phase. With that all set, I'd like to briefly go through each of the studies. And the first study is to standardize Canadian terrain data at multiple resolutions by using DGGS. Here's the workflow. So after we acquire the raw data from their endpoints, we do pre-processing, which means to standardize both the horizontal and the vertical datums. Then the quantization means to firstly find out the cell sundries at various levels, then resample them with the bilinear interpolation. And if the cell got two different elevation values from two original data source, then we do integration by giving more priority to the high resolution DEM. We also did aggregation, which means to calculate the mean, maximum, and minimum values of the chopped cells and assign that to their parent cell at the coarser level. And quality control was carried out by comparing the values from ground control points and pre-DGGS values and post-DGGS values. We did experiment in 2 study areas in Ontario, Canada. As you can notice here, the blue rectangles are the spatial distribution of the HRDM, the high resolution DEM. And the CDEM is available in a 4x10. And here's the results of visualization. The integration of the both data sets over 2 study areas at the level 29, which is the finest level in my experiment. If you like to know more details about the methods or the results, please refer to our paper here. So the second study is to develop analytical functions based on terrain data modeling DGGS. We also extend Tomlin's theory regarding map algebra proposed in 1990s into a DGGS context. So here are all the functions we've been developing in the DGGS. And I generally classify them into 4 categories. Here, the focal statistics and zonal statistics include all kinds of discrete stats that calculated based on a neighborhood of a cell or a defined zone. And topographic analysis include those classic topographic parameters like slope aspect, gradient, curvature, and hill shade. The hydrological analysis are those functions like flow direction, flow accumulation, watershed, etc. And there are, we identified a few key points that may open for discussion, like how do we assign flow directions over hexagons, how do we treat pits and flat areas over hexagonal grids, and how do we do parallel computation, for example, by the flow branches, if one would like to improve the computation time. Then we generated 4 topographic indices. We also extend the Tomlin's model regarding the map algebra into DGGS context. So they are local operations, zonal operations, focal operations, and global operations. we do have defined the fourth class here. So among them, the local and the zonal operations are relatively straightforward. They are just computation that based on a single cell or a defined zone. The focal operations are the computations based on within a neighborhood of a cell, where the neighbor navigation should be necessary for any focal operations. So for our study, we took advantage of the QTDR indexing that has been implemented in the Discrete library. So it helps to locate the neighbor of each of the cells based on their coordinate-like index. Then we classify those computations that need recursion in their production, like flow accumulation and watershed, into the fourth class called global operations. Then the experiment was carried out in 3 study areas in Alberta, Canada. And here are the visualization results of one of the study areas, the Canmore area at level 24. So as you can see here, they're the visualization of mean elevation, hill shade, standard elevation, slope gradient, and the watershed, the delimited watershed over a defined outlet. So lastly, the third study is to model flood susceptibility by machine learning in the DBGS over multiple resolutions. And the methods and results from the first 2 studies will be used in the third study. The workflow here just follows the classic workflow of any machine learning analysis. And the only difference is the predictor variables will be quantized in DGS first, and the analysis will be carried out in multiple scales. We also have cooperation with the Natural Resource Canada, and they're doing the parallel analysis with traditional GIS. So it's very likely we can compare our results at the end. So let's wrap up by 3 research impact here. Firstly, we explore the utility of DBGS as an integration platform of multi-source data, and that is potential for a national elevation service for Canada. And secondly, we've been developing analytical functions in a pure DBGS environment. Specifically, we migrate those square-based algorithms to the hexagonal grids. And finally, we'll investigate the DBGS-driven decision-making in the real world. And specifically, we'll do fault mapping and machine learning in the DBGS. And that's it from me. I would like to pass it over to David.
Thanks, Erin. Okay, let me just share my screen here. One second. Okay. Okay, so I am going to discuss some of the research outcomes that we've recently had and future directions. So more specifically, I will look at the research outcomes that we had when we studied our HailPix DGGS, in particular with regards to orientation and latitudinal data analysis. And then I will move on to the end of this presentation to talk about an interesting research direction, that is the link between DGGS and spatial networks. So firstly, as Marta highlighted previously, one of the design choices when constructing a DGGS is how to orient the polyhedron relative to the Earth. So for example, if we consider the spherical icosahedron, there are different options. We could orient it with vertices at the poles and an edge aligned with a prime meridian, or alternatively, we could orient it such that all vertices form the ocean. and there are pros and cons and reasons for each. But aside from a global scale, national or regional administrators may also find it beneficial to adopt a DGGS framework to reference the large volumes of data encompassed within their boundaries. Therefore, we should consider DGGS orientation at a local scale. So here, these images just try to show that in this case, the icosahedron can be rotated and translated to ensure that the study area, whether it's Canada or China, can be optimally placed within a single face. So we were interested in this idea when we were studying the RHLPX DGGS, in particular how it could be orientated to suit different regions at a local scale. So for those of you not familiar with this DGGS, it is a quadrilateral based approach that is constructed essentially by projecting an ellipsoid such as WGS84 onto the 6 faces of a cube, partitioning each face into square grids, and then ultimately inversely projecting those cells back onto the ellipsoid. However, this construction approach results in essentially 2 regions and variable cell shapes and cell orientations. So in a nutshell, we have the equatorial region, which is in between roughly plus or minus 42 degrees latitude. And here, cells are bounded by 2 parallels and 2 meridians. But in the polar regions, we have this issue with variable cell shapes. So we could have a circular polar cap cell, but also dart cells and quad cells that are north-south aligned and slanted. So this slide just tries to highlight some of those options. So for example, Texas falls in the equatorial region. So here we have the nice property that all cells are, or quad cells, are bounded by 2 parallels and 2 meridians. However, in the North Polar region, for example, where Canada lies, we would have this situation where some regions may be covered by quad cells that are north-south aligned, whereas other regions are still covered by quad cells, but they would be slanted to some degree. Another issue that we would potentially come across was, let's say, if the region of interest falls across the border of these 2 regions, as New Zealand does. So here we can see that the north part of the country falls in the equatorial region. So we have north-south aligned quad cells, but at the boundary, we see that in the south region, polar region, the quad cells are slanted, and you get this abrupt transition. So what we showed was that, in fact, you can rotate the RHLPX DGGS to suit different regions at a local scale. And we were interested in Canada specifically, and we showed that for smaller regions, such as here in the province of New Brunswick, we could in fact create north-south aligned quadrilateral grids. But for Canada as a whole, because of the large east-west extent, we would always have to face the different orientation of quad cells. Although we could shift triangular dart cells to the Alaskan border, let's say. So moving on to latitudinal data analysis. Now, I just wanted to mention this because while we were studying the RHLPX DGGS, we realized that it has this rare and interesting property, and that being, you can probably see here on this image that cells, let's say, are distributed nicely along rings of constant latitude, which is often referred to as isolatitude rings. And this led us to wonder if we could utilize this property to facilitate latitudinal data analysis, which had recently been shown to reveal interesting patterns, particularly when analyzing population, environmental, social and economic data. And I picked out these 2 images from the study of Kumar and Boris, just to highlight that we can easily see here, population is pretty much dominated in the Northern Hemisphere, around 30 degrees latitude. We can also see, I think it's GDP per capita, how that changes on the north-south axis. But also, if we look at CO2 emissions, it resembles very closely the pattern of GDP per capita. So based on these interesting patterns and this type of analysis, we went back to the RHLPX DGS and thought, okay, this type of DGS has some interesting properties that can facilitate this type of analysis. So I've just mentioned that cells are distributed along rings of constant latitude, but also cells have equal area. So we can avoid some of the normalization by area issues that you might come across with using a geographic grid. And as a DGS structure, we already know, for example, that Perry discussed, it enables efficient integration of large volumes of heterogeneous data, whether it's population data or economic data. And it also supports multi-resolution analysis. So with that in mind, we developed methods to manipulate the cell identifiers directly in order to determine which isolatitude ring the cell falls on. And using these algorithms, we demonstrated the feasibility of using the R-Helpix DGS for this type of analysis using 2015 population data for roughly 500,000 locations across Canada. And here I just highlighted a couple of images that show the capabilities of multi-resolution analysis, where we can see how the population changes from north to south. And we can also see how we can visualize results on the globe as well. So I will end my part of the presentation by looking or highlighting an interesting research direction that is gaining attention, and that is the link between DGGS and spatial networks. So in particular, there appears to be a growing interest lately in using DGGS to construct spatial networks, as well as to analyze and visualize the data at both global and local scales. So just to highlight this growing interest, I've picked out 4 examples just to briefly highlight here. So if we consider 2020, Ferreira et al., they used a DGGS to convert global spatial temporal data, I think in this case it was fire events, into a network representation whereby network nodes are represented by grid cells and edges connected nodes with successive fire events. And they did this in order to support spatial data mining tasks, such as community detection and anomaly detection. More recently, in 2021, there was a study that used a DGGS to support geoprivacy needs of users, for example, by using cells to introduce uncertainty into a user's location when sharing spatio-temporal data, in this case, socio-spatial networks. Back in a couple of years ago, 2019, Raposo highlighted the potential of using a DGGS to visualize large volumes of origin destination data at different spatial resolutions in support of the growing interest in mobility network studies. And lastly, I'm sure everyone has heard of Uber, but maybe not everybody knows that they have also adopted a DGGS to support the analysis, visualization, and exploration of all of their urban mobility data. So overall, this work just highlights that, in fact, DGGS do have the potential to open the door to interesting studies in new and exciting domains. And one research direction that we have an interest in right now is further exploring the benefits of using a DGGS to support the study of mobility networks, especially at the urban scale. Now, in recent years, the study of these networks has attracted a lot of attention due to the growing availability of large volumes of fine-grained individual level data, whether it's from social media data, mobile phone records, or car GPS data. For example, here, I think this is 1.1 billion trips in New York City. You can see the distribution of origins and the distribution of destinations. But to study this data, it is often aggregated into a regular grid of fine resolution cells to create an origin destination network, as shown here. I think this is car trajectories in Rome. So with that in mind, how could a DGGS support these studies in terms of integration, OD network construction, analysis, and visualization? So this slide highlights some of the potential benefits that we foresee. So I'll just run through this here. So in terms of integration, we know from Harry's talk that a DGGS is highly efficient and suitable for this process. So we can easily integrate lots of origins and destinations into a DGGS framework. Then in terms of OD network construction, we need to create a grid. The DGGS allows us to create this OD network at multi-resolutions, as well as even at variable resolutions. Hopefully you can see here that the cells are at different sizes. Moving on from that, then we need to analyze network, analyze the network using different metrics. So for example, there's recent interest in centrality measures in particular that not only determine the most important locations based on the trips, but also based on lots of other information in the urban area, such as point of interest information, that's particularly popular at the moment, as well as raster information, let's say land use cover. A DGGS can efficiently integrate all of this heterogeneous data into a unified framework. Moving on from analysis to visualization, because of the multi-resolution properties, we can visualize hotspot locations and the spatial characteristics of those hotspots at different resolutions. And then going even further, because the DGGS framework is a global structure, we can repeat this type of study for any urban environment on the planet, obviously assuming we have the data. And by doing this, it would allow us to identify broader patterns, trends that would ultimately improve our understanding on urban mobility and urban environments more generally. So I will end it on that note, something to think about, and I'll pass back to Perry.
Yeah, thank you, David. That was wonderful. I think that I would just take that statement off and continue with it as, you know, as photogrammetrists or image processing engineers, as GIS professionals, we often are conflating data and doing it on a grid of our choosing. And so one might ask, well, why do I need this? Because, you know, I just pick the grid I want when I want to. And but David makes a good point. You know, when you're using a DGGS, you're actually developing your algorithms on the data structure, the grid itself, independent or agnostic to the data that you're going to populate it. So you can write your algorithm for a certain location and then move over to another location, just populate the data, might be from a different source even, and make some adjustments. So I think that's a really important point that David's made. So what I want to do is kind of leave you with transition from that. There's sort of the more traditional way of looking at image processing and analysis, spatial analysis, and take us into a future world of what we would see DGGS playing a central point in. So we kind of have two models of use here. One is this traditional process-based analysis. And that's what we're familiar with. We're taking different data sources, we're integrating them, we're putting them through a number of processes. In that type of analysis, if we're presenting software that uses that, we need to really communicate with the people that are developing the software to be able to understand that software. We have to be highly educated, really, technically, in how that software works. We can become, you know, if we know that software, it's really hard for us to go off and use another piece of software because we have knowledge or domain knowledge. Why we get paid is because we understand how that process works. So I call that process-based analysis. I'll just review that a little bit and how that works in a DGGS, because we're not throwing away process-based analysis with DGGS, as David and Erin have also shown. But I also want to introduce a new way of thinking of spatial analysis, more from as a communication model as opposed to an analysis model. And I call that discovery-based analysis. And that should be our end. We'll end on that vision. So if we're talking about DGGS and process-based analysis, and I'm just restating really some things that Erin and David brought up, we're going to do a traditional flow of information, a pipe and filter. We're going to access data sources of different kinds. We're going to quantize and sample them into the grid. And we're going to write inputs and outputs, little processes that do things for us, and we can string those all together. And the picture on this slide shows a comprehensive pipe and filter that results in the demonstration that I provided earlier. So essentially, that XML file full of processes being done on the fly as we integrate data. And we can come in and we can customize those little processes and do all the nice little things we do as big things sometimes for processing data, Fourier transforms or something like that. I like to think of DGGS operations as really 4 basic atomic, mutually independent processes. One is iteration. And if we think of this from a traditional database, this would be like iterating through indices, going from how we quickly transform along those indices. And in a DGGS, we have that same kind of functionality. We can go horizontally and vertically. It's navigation, right? Zooming in and zooming out, panning. And this is be able to very quickly move along those cells and select those cells, just like we do in a database. And that's why the indexing is so important, the ability to do that. Searching, broad searching, depth of searching. So any processes that are doing that are really iteration. And then we have calculation. I think calculation, this is a cell-based process where you have one cell and you're either creating or modifying an existing value in that cell. So that's a calculator. If I've got average temperature for 2020, and I've modeled the temperature for 2050, I can do a climate change across the globe by doing a calculation process, by taking the second one and subtracting the other one. I can see how the temperature is going to change across the planet in different locations. That'd be a calculation process. A selection process is a cell that we select. So a bunch of cells, so I could do a bounding box and aggregate those cells. Or as Erin has showed, I could do a watershed. I could say, delineate a watershed. Now I have a collection of cells. They don't have to have any data values in it. So any process that produces a collection of cells, what might be called geometry, is a selection process. And then that final, and she talked about the traditional model of, local, focal, zonal, global. That really works out on a DGGS because we have a real global phenomena. We have the whole globe as a domain. And then finally, if we have data values in the cells and we do an aggregation, we can do statistical summaries of that data. And that really is describing the phenomena that we've selected using the selection process. So within that watershed, what's the average rainfall? Or if we have a storm coming, what's going to be the distribution of flow? We could do a little model, rainfall, runoff. We could do a backwater calculation. Well, all those things we would traditionally do. It's not that we could do something new here, but it's all on a globe, in a common environment, a common framework, as David has said. So that's kind of the way I would see a DGGS process-based analysis works. And I've got a list on this slide of examples of these processes that are working in these operations. Now, so this is kind of a workflow for watershed. Now, so what's new under the sun? Who cares about DGGS? We could do that already using our own software. Well, one of the things that happens is the hardest job we have is to aggregate or fuse or combine geospatial information. it's the most expensive part of our analysis process, other than acquiring data, is often I spend 90% of my budget on bringing all the data sets together before I can even start doing some analysis. So what happens to our world when we don't have to worry about that anymore? You know, 90% of our budget sometimes, I often talk to people, it's always like, it's a big number. If we take that away, you know, we're doing data mining operations, we could actually start to get other people involved in the process. The decision makers themselves are often quite competent about the question they want to ask. And a biologist, for example, they know what question they want to ask. They just don't know how to integrate data, so that they could ask an SQL statement, and they could do that. So this opens up a world of more people being able to do spatial analysis. What I want to show you here is that we can actually enable young children to do pretty comprehensive spatial analysis. Just one click, as you saw on my demo, I was really just one pick, and I was able to aggregate and report on different factors. This actually recasts, if you think about it, spatial analysis as a communication model. Something that I'm interested in as part of my studies is, what does it mean when we're looking at this as a communication model, not a spatial analysis? And then we have a kind of a new model that sets up. So here's a picture of sort of what functions you've seen. We have some open services. We can aggregate that analysis ready data, and the user can, you know, explore the data sources. What this also opens up, some future, this is the vision, is that our users can now interact with a globe and start to ask it questions. Fundamentally, I find there's two basic spatial questions that the user is wanting when they're exploring. What is here? Select an area, report, tell me what's going on there. What's the average house prices? What's the average elevations? The other question is, where is something? Where can I find the highest elevation in the world? Where could I find this condition, this condition, this condition, but not this condition? You know, let's zoom to that place on the planet, or show in red all the places where I should go fishing this summer because it's nice weather there. So this is the kind of interaction that opens up traditional spatial analysis to everybody. Everybody now has the ability to do that. It's kind of this communication model becomes discovery-based analysis. It's the way we like to go into Wikipedia and browse around for information. So in my studies, I'm really looking at creating this autonomous digital Earth vision. There was a speech written for Al Gore in 1998, I believe, where he talked about children being able to explore the planet, aggregating pretty sophisticated data sets, adding their own data, and then sharing that with their friends. This is a vision for digital Earth. And it's part of our work that we're doing at the University of Calgary in the Geomatics engineering department, trying to enable this future. So we had the opportunity to bring together 7 schools in the Calgary, city of Calgary area of 10-year-olds and 12-year-olds. And we just gave them some software to play around with DGGS software. And we asked them afterwards, how did it go? And these are 10-year-old children. I want to emphasize, they're 10 years old, they're in grade 5. And we put some laptops in front of them and said, go at it. I hope this comes across okay.
I was looking at Canadian resources and where they are throughout the provinces. If it would be better to find gold on a higher level or a lower level. And then I like the fact that you could overlap layers on top of each other and not just look at one layer at a time. So that way you can have all the gold mines on top of the provinces so you can see where they are. You could search pretty much anything I wanted to sort of look at, what different things you could do with it. I wanted to look at, tourist attractions or just things like how this could be useful if you were just a traveler. Maybe you wanted to go to New York and you wanted to see, and you wanted to look at some of the good hotels to go there or the good food places. I liked how there's so many different settings and so many different things you could do with it. Like you could figure out the populations, religions, males, females, age groups, which is so cool, and you can go really far with that. And I think this would be super useful just in the school. So it can be really useful for learning lots of things in the school. It could probably have many, many uses just everywhere. It's really cool.
So Emmanuel, that sort of ends my presentation.
Yeah, thank you, Perry. That was really nice. So there is a question. You actually answered this implicitly, but if you wanted to comment a little bit more, what are the challenges for the global adoption of DGGS at this moment?
Well, first of all, I have to say I feel it's inevitable because we spend so much money right now on data integration, and there are so many people that want to do spatial analysis, but we have this intermediary, I guess it's us, Geomatics professionals that have taken over the job. I think it's kind of inevitable that we'll be disintermediated and relegated to other probably more important things like looking after the data sometime. I mean, I can't imagine 100 years from now we won't have a system like this. But that doesn't really answer the question. Adoption comes sometimes is usually disruptive. It's very difficult to predict, where adoption will come from, and it's a difficult problem for sure, because people who are professional marketers really have, if they had that ability just to say, this is what we're going to do, they would. I would find, though, the characteristics are it's probably going to be somebody that's not in the field right now or a group of people. It'll be like these children. It's not going to be GIS professionals who are going to pick this up and adopt it and say, this is the thing to do. I think it's useful for GIS professionals. I think we should have to be aware of it. We can be champions of it. If we're GIS professionals, we probably have a job where people are coming in and bugging us all the time for some really small problem. And this will seem like a toy for us anyway. So why don't we just give them that toy and they'll go off and start to discover things. That's often how disruption happens. I don't know if that answers your question. It might be somebody comes up with a really nice open source solution. Maybe it's implemented. Uber's an example. I'm not a big fan of their DGGS because it works well for localized areas, but it's not a global system. But it's being adopted because there's open source and software developers can get at it and start to play. I think that's an important part of it.
Thank you, Perry.
Yeah. Anybody else want to answer that?
So are there any other questions? You may probably type your questions. We haven't seen any new questions in either the Q&A or the chat window, but please type your question if you have any. Well, thank you very much, everyone, for first of all, our speakers and our presenters for their excellent presentations, and also the audience, and for your interest in DGGS and the work that we have been doing at the University of Calgary. You know how you can find us and how you connect with us. You can email us and we can continue this conversation. A big thank you also to the hosts of this webinar. I know that some of them are connecting from Asia, and it's already midnight or even later than midnight. So thank you all, and we wish you all the best for the new year.